Welcome to This Explainer. Today we're diving into something that literally shapes the entire physical world around us. Have you ever stopped to wonder why a swinging pendulum, an electrical circuit, and even the atoms inside a solid crystal all seem to follow the exact same mathematical rules? Well, we're going to unmask the grand, universal heartbeat that governs almost every single vibration in the universe. All right, let's jump right in.
Here's our roadmap for today. First, the universal law of oscillation. Then, the shadow of the circle. Third, springs, pendulums, and circuits. Moving on to energy and motion, and finally, damping and resonance. It's going to be a fun journey, from abstract physics to some pretty chaotic real-world realities.
Okay, part 1, the universal law of oscillation.
To kick things off, we really have to tackle a massive question. Why on earth do radically different systems all seem to vibrate in the exact same way? Well, it all comes down to potential energy. Imagine an arbitrary, really complex potential energy curve. Let's just call it U of x, with a local minimum right there at the bottom. If a particle is sitting in that dip, it's at a point of stable equilibrium. If you give it a tiny push, it gets trapped. It's kind of constrained to that small region purely because it doesn't have the energy to climb back out. And honestly, this is where nature plays a brilliant trick on us.
Since the particle only ever explores that tiny little area around the minimum, we actually don't need to care about the wildly complicated shape of the entire energy curve. We can use a mathematical tool called a Taylor expansion. Notice that green dashed line centered right on the minimum point? We use that to approximate the immediate area. Basically, we take this crazy wiggly curve and effectively just chop off all the complicated math that happens far away.
And look what happens when we do that. The math beautifully, and I mean perfectly, collapses into a simple parabola. Now, if you've done any mechanics, you'll immediately recognize that a parabolic potential energy curve is exactly what defines a standard Hooke's law spring. So the absolute crucial takeaway here is this. Any system, no matter how ridiculously complex, if it's near a stable equilibrium, it fundamentally behaves exactly like a mass on a simple spring. This mathematical truth right here is why the harmonic oscillator is arguably one of the most important concepts in all of physics.
Which brings us to part 2, the shadow of the circle.
Now that we've got the algebraic truth locked down, let's translate this into geometric motion that we can actually visualize. This brings us to simple harmonic motion, or SHM. By definition, we're talking about sinusoidal oscillations about an equilibrium point, featuring a constant amplitude and a constant frequency that is totally independent of that amplitude. This physical motion is the direct, real-world result of that parabolic potential well we were just looking at. But what does it actually look like in practice?
To truly visualize this, I want you to imagine a vertical disc rotating at a perfectly constant speed, and it's got a small peg stuck on the edge. Now shine a light straight down from above to cast a shadow of that peg onto the floor. If you ignore the disc and just watch that shadow moving back and forth, it perfectly traces the exact motion of a mass bouncing on a spring. It's amazing. The two-dimensional circular motion flawlessly projects into a one-dimensional simple harmonic oscillation.
Now, to talk about this motion, we need a universal language, right? Our kinematic vocabulary. Amplitude is the maximum displacement from the center, basically how far our shadow travels. Angular frequency, well, that's how fast that wheel is spinning, usually measured in radians per second. Period is the time it takes to complete one full cycle, and phase just tells us the starting position on the wave the exact moment we start our stopwatch. These 4 variables are literally all we need to describe any oscillating system.
Moving on to part 3, springs, pendulums, and circuits.
Let's populate our physical world and actually prove these math rules apply to everyday objects. We'll start with the absolute classic, a point mass on a massless string. When swung at small angles, it undergoes perfect simple harmonic motion. And what's really fascinating here is the math. The period relies entirely on the acceleration of gravity and the length of the string. It completely, 100% ignores the mass. You could put a bowling ball and a feather on the exact same string, and they would swing at the exact same rate. It's purely geometry.
But what happens when things get a bit more complicated? Well, as a classic MIT mechanics lecture points out, even a system as bizarre as a hula hoop, which oscillates about a pin, can now be calculated very easily with the knowledge that we have. By using something called the parallel axis theorem, we can take the messy, distributed mass of a complex physical pendulum, like a hula hoop or a ruler or really anything, calculate its moment of inertia, and just apply our simple harmonic math to find its period. The exact same universal laws apply.
And the crazy part?
It goes way, way beyond mechanical objects. Check out this direct cross-disciplinary parallel. In an electromagnetic RLC circuit, the physical mass mathematically mirrors the inductance. The spring constant, that matches the inverse capacitance. Even physical velocity becomes electrical current. It absolutely proves the universality of this equation. An engineer designing a radio is literally using the exact same math as an engineer designing a car suspension. It's the same math.
All right, part 4, energy in motion.
So what exactly fuels this perpetual dance? Well, it's all about the relentless conversion of energy. Think about how the flow works. You've got position, potential energy, and kinetic energy, and they all oscillate completely out of phase with each other. When a spring stretches to its absolute maximum, it actually stops for a split second, meaning it has 100% potential energy. But as it snaps back and rushes past the exact center, potential drops to 0 and kinetic hits 100%.
So, the forms of energy are constantly trading places over and over again. But here's the critical takeaway. In an ideal system with no friction, if you add the potential and kinetic energy together at any given exact moment, the total mechanical energy remains absolutely, perfectly constant. It never changes. E equals 1/2 Ka squared. Simple as that.
And finally, part 5, damping and resonance.
Of course, we don't live in a pristine, frictionless void. We have to introduce a little real-world chaos to our mathematical model. When we add a non-conservative drag force, like air resistance or friction, it slowly robs the system of energy, forcing the amplitude to exponentially decay. And we see 3 distinct regimes here. Underdamped systems slowly decay while still oscillating back and forth. Critically damped systems return to equilibrium as fast as physically possible without crossing the center. This is exactly how your car's shock absorbers work. And overdamped is just a sluggish, slow return without ever oscillating. But what if, instead of just losing energy to friction, we pump energy in? This leads us to the incredible phenomenon of resonance. This happens when the frequency of an external driving force perfectly matches the natural frequency of the oscillator. When you time your pushes perfectly, think of pushing a kid on a playground swing, you completely cancel out that damping friction and feed boundless energy into the system. This causes the amplitude to dramatically and sometimes even violently spike.
Resonance actually has a breathtaking duality in our world. On the constructive side, it's literally how we tune a radio. We adjust the electrical resonance of the circuit to plug a single specific frequency out of thin air. It's also the basis for the hyper-accuracy of atomic clocks. But on the destructive side, well, if the wind happens to push a structure at its natural frequency, it can cause catastrophic destructive vibrations. A perfect example of this is the infamous collapse of the Tacoma Narrow Suspension Bridge.
We have covered a lot of ground in this explainer today, from the Taylor expansion of a potential well to the swinging of a pendulum and the tuning of a circuit. The universal law of the harmonic oscillator is quite literally everywhere. So I'll leave you with this. Look around your room right now. Based on what we've learned about stable equilibrium today, what hidden harmonic oscillators are secretly vibrating right in front of you, just waiting to be noticed? Thanks for joining me, and keep observing the amazing world around you.